Implicit differentiation starts on page 141. So first, let's learn why we need implicit differentiation. It says, up to this point in the text, most functions have been expressed in explicit form. For example, in the equation y equals 3x squared minus 5, the variable y is explicitly written as a function of x. So that's what an explicit function is. It's solved for y. Some functions, however, are only implied by an equation. For instance, the function y equals 1 over x is defined implicitly by the equation xy equals 1. So all you've got to do to change an explicit function to an implicit one is to have it, write it so that it's not solved for y anymore. Okay? So when it's solved for y, it's an explicit function. When it's not solved for y, it's an implicit function. It's the same equation, so it's the same function. It's just written in a different form. Suppose you were asked to find dy dx, that's the derivative of y with respect to x, for this equation. You could begin by writing y explicitly as a function of x and then differentiating. And in fact, if implicit differentiation did not exist, that's what we would have to do. So we would start with xy equals 1. We'd say, okay, we got to have it solved for y so we can take the derivative. So we would solve it for y and simplify it and put it in a form easy to take the derivative of. Then we would take the derivative and simplify it. Nothing wrong with that. Other than it doesn't always work. This strategy works whenever you can solve for the function explicitly. You cannot, however, use this procedure when you are unable to solve for y as a function of x. For instance, how would you find dy dx for the equation? And look at that equation. X squared minus 2y cubed plus 4y equals 2. Where it is very difficult to express y as a function of x explicitly. So, mathematicians back in the day realized that not all functions are nice, easy, y equals mx plus b, and you can't always then do what we've been doing with derivatives. Yeah?
Y is like explicit on y solely by itself. Right?
Correct. And notice, too, before we get into this any further, the implicit form and the explicit form, all right, they're equivalent. They're the same equation written in different forms. So look, y is a function of x, isn't it? It is. It equals 1 over x. So y, even if it's not solved for y is still a function of x. It's just, we just don't know what that is. I don't know what it is there, do you? Y is a function of x. All right, we can plot points and everything, can't we? We can make a little xy chart, make up an x coordinate, figure out what y must equal, and do that, and plot points and graph it. We can do all that. But I don't know what the function y equals. I don't know. Okay? All right. So, when we have this, and the function is very difficult, or maybe just flat out impossible to solve for y, we have to use implicit differentiation. Now, to understand how to find dy dx implicitly, you must realize that the differentiation is taking place with respect to x. That's why implicit differentiation is usually introduced to you the way it's introduced to you today, which is by calling it dy dx. There are other notations we can use for derivative, aren't there? But we're using the notation dy dx to try to drill into your little head, hey, it's a function of y, but the derivative is with respect to x. dy, it's a function of y, or, well, y is the name of the function, dx with respect to x. Okay? Now, this means that when you differentiate terms involving x alone, you can differentiate as usual. So, if I was taking the derivative of what's shown there at the top of the screen, x squared minus 2y cubed plus 4y equals 2, to take the derivative of x squared, it's 2x, just like we've known for a while it is. Okay? Because that's written as a function of x. We're good. X is the variable, right? If x is the variable, that's what we've been doing up until now. So that doesn't change. However, when you differentiate terms involving y, you must apply the chain rule. And a little more information, or product rule, quotient rule, whatever applies. Okay? Because you are assuming, and we're not assuming, because we know that y is defined implicitly as a differentiable function of x. So, y is not a variable. Y is the name of the function. Okay? Isn't y the name of the function? Now, I say it's not a variable. I mean, you can still make ordered pairs, and you can treat it as a variable when you're making ordered pairs, plotting points, can't you? All right? But y is the name of the function. So just because it's written like this instead doesn't mean that it's no longer the name of the function. It's still the name of the function. Okay? So you must treat y as a function. All right. You think you're with me so far? Yeah. Yeah, and see if we did that, if you replaced y right there with 1 over x, isn't x times 1 over x equal to 1? So it's still true, isn't it? It all still holds together. Okay? Now, I'm using that example because this is one where we know what y equals. But an example like this, I have no clue what y equals. If I could figure out what y equals with a step or two, I would. And I wouldn't bother with implicit differentiation. But I can't. That's the whole issue. Okay? All right, a couple things that I'd like to add to what the book tells you. Actually, this isn't an add. This is a rewording, barely. It's a little bit of a paraphrase. It says, use implicit differentiation when it is difficult or impossible to solve the equation for y. Remember, the derivative is with respect to y. Differentiate terms involving x as usual, just like you always have. Use whatever rules apply. Since y is a function of x, we must apply the chain rule or the product rule or the quotient rule, whatever applies when differentiating terms involving y. Y is a function. Treat it like a function, not a variable. X is the variable, y is the function. Okay? Let's see. Now, the graph of an implicit function might actually fail the vertical line test. Okay? In fact, even if you don't have the graph, but that's the easiest way to tell, what we're calling implicit functions may actually be a family of functions. For instance, what would you get if you graphed x squared plus y squared equals 4? What shape would you get? Get a circle. Okay? You get a circle. Its center's at 0, 0, and its radius is 2. That's not the graph of a function, is it? But look, now, and again, I chose one that actually could solve for y, okay? If you do solve that for y, you get two different functions of y, each of them a semicircle. Well, that passes the vertical line test. That's a function. That passes the vertical line test. That's a function. Oh, you know what I was hoping it would let me do, right?
Yeah.
Pretty close.
Yeah. So, just because, moral of the story, the equation you're dealing with may not be an actual function in and of itself. It may be, like this one, two functions. Hey, that makes implicit differentiation twice as nice, because if we did solve that for y, and then take the derivative. We'd have to do it for two different functions. Whereas after I teach you how to do implicit differentiation, you're done in one step. Well, not one step. You only have to do one derivative, though. Okay? So, our equations that we're calling implicit functions may actually be a family of functions. Okay? All right. Now, these guidelines, which are on page 142, will actually make more sense after I've worked an example or two, but they're on page 142. We're going to differentiate both sides of the equation with respect to x. Then we're going to solve it for dy dx. Okay? So, differentiate, solve for dy dx. And that's what steps 2, 3, and 4 are, the steps that you have to go through to solve for dy dx. Let's begin with number 2. The directions say, on page 146, find dy dx by implicit differentiation. Now, I have found over the years that sometimes, even though dy dx really is the best notation to use for implicit differentiation, what I've found over the years is that students won't use it because y prime's faster. Y'all don't know anybody like that, do you?
No.
So a lot of times, and in fact, right here, look, I'm going to use y prime because that's what you're probably going to write anyway. When we get to the next section, related rates, I'll stick with the dy dx almost exclusively. Okay? So for now, if you want to use y prime, fine. If you want to use dy dx, fine. You got to remember, x is the variable, y is the function. Okay? All right, number 2. We're going to find the derivative by using implicit differentiation. What's the derivative of x squared been for weeks now? 2x. So, oh, and by the way, I always put a therefore when I start doing implicit differentiation. If nothing else, it's a heads up from me to you that I didn't do algebra to get this step. I did something else. I did implicit differentiation. Okay? Now, copy down the minus sign. Y squared. Y is a function. Hey, when we did the chain rule, didn't we call u? Didn't we let things that were quantities, things that were functions of x, didn't we call those u? So if we were taking the derivative of u squared, wouldn't that be 2u to the 2 minus 1 times the derivative of u? That's what we're doing. So the derivative of y squared is 2, and then our function y, oops, I erased too much. You've seen too much. So it's 2u, 2y, subtract 1 from the exponent, 2 minus 1 is 1, times the derivative of u, the derivative of y. Well, the derivative of y is either dy dx or y prime. All right, the derivative of the equal sign is equals. I never taught you that. Now you know. And what's the derivative of 16?
7.
Any questions? And what did we use to find the derivative of y squared? We used the chain rule. How come? Because y is a function, not a variable. All right. Now we solve it for y prime. You do whatever steps you got to do. If you have more than one y prime, you would want to get them together, combine like terms, which almost never works, but that's what you'd like to do. You put all the other stuff on the other side, right? Well, so let's put all the other stuff on the other side. Let's subtract 2x from both sides, and we'll get negative 2y y prime equals negative 2x. And now to get y prime by itself, y prime is what we're solving for. To get y prime by itself, I need to divide by negative 2y. Well, negative 2x divided by negative 2y, negative 2's cancel out, right? They divide out. Negative 2 divided by negative 2 is 1. So I just get x over y. So y prime, or dy dx, equals x over y. All right, before we go to the next example, a derivative is still a formula to find the slope of the tangent line. It's still a formula to find the rate of change. It's still a formula to find the velocity of a moving object. What's different about this formula than every formula we've come up with up until this moment? There's a y in it. Okay? Up until now, if they gave us a point to use to find the slope of the tangent line, we always ignored the y, didn't we? It didn't matter. Does it matter now? It matters now. All right, any questions on number 2? Number 6. We're still going to use implicit differentiation. This time we have x squared y plus y squared x equals negative 2. X squared y plus y squared x equals negative 2. It is scary. You know how near Halloween they always have a lot of scary movies on TV? They should have this. Hey, I could just post these as scary movies. All right, x squared y. To take the derivative of x squared y, we have to use the product rule, because haven't we always done first function times derivative of second plus second function times derivative of the first? That's what we got to do. So, derivative of x squared y, first function, times the derivative of the second function. What are we going to call the derivative of y? Plus the second function, y, hang on, no. The second function, y, times the derivative of the first. What's the derivative of x squared? So what we have showing there is the derivative of x squared y. First function times the derivative of the second plus the second function times the derivative of the first. So we treated x, or in this case x squared, like we always would have in the product rule, and we treated y as a function because it's a function. Plus, now we take the derivative of y squared x. All right, the derivative of y squared. You got to chain rule it, don't you? So now I'm doing product rule, right? First function times the derivative of the second plus second function times derivative of the first. I've already taken care of that. I'm looking at this. So product rule on what I have underlined. First function, y squared, times the derivative of the second. What's the derivative of x? 1, plus the second function times the derivative of the first. Now, to take the derivative of y squared, chain rule it. So 2y, subtract 1 from the exponent, times the derivative of y, because it's a function. And what do we get on the other side? The red goes with the red, the blue goes with the blue. The green goes with the green. Alex? All right, once we got to here, we were taking the derivative of that. So, if it was this, we'd get 2u times the derivative of u, wouldn't we? So we get 2y times the derivative of y. Because right here we're using the product rule, so it's first function y squared times the derivative of the second. Derivative of x is 1. That's the second function times the derivative of the first. All right? Everybody stared at it long enough? All right. Our goal now is to solve it for the derivative. So solve it for dy dx or y prime, whichever you've used. So before we do that, before we solve, we simplify. Now, x squared y prime is just fine as x squared y prime. But y2x, that's just weird. Call that 2xy. Y squared times 1 is y squared. And x2y prime is also weird, so make that 2xy y prime. Whenever you have y prime as a factor in a term, put it last. Put it last. Okay? Now, I'm trying to solve for y prime. I have two terms with the y prime in them. Do what? Yeah, in just a second. Before we factor by grouping, though, we're going to... Okay? So, I've got x squared y prime and 2xy y prime right where I want them. So leave them on the left. Now, when you move the 2xy and the y squared over to the other side, you can either do what I did, which is group them together and put a negative in front. So I thought of it this way. I thought of that as a group. I subtracted that group from both sides. Or, if you don't want to write it that way, then just write it that way. It doesn't matter. It does not matter. You follow me? Now, on the left side, what I'd like to do is combine like terms, right? Back in good old Algebra 1 days, if you had a 3x plus 4x on the left, you'd add them together and get a 7x. Well, we'd like to do that with our y prime terms, but we can't because, wow, this is a mess, because they're not like terms. So instead, since they both contain a y prime, factor it out. So on the left side, we factor out that y prime. We get y prime times the quantity, x squared plus 2xy. And we almost have y prime all by itself, don't we? All we got to do now is divide both sides by x squared plus 2xy. That's it. Now, we could factor a y from the numerator and an x from the denominator, but that nothing divides out. So, I'm just really happy if you get this far. Aren't you?
Yeah.
Without tears. I'll make it there without tears in under 30 minutes.
I don't even care if you cry.
I know you.
Yeah, we're to that point. I've accepted the fact you're going to cry. So, I think it's fun too. I hope you don't think it's too fun because you might end up being a math major and doing this for a living, and I wouldn't wish that on anybody because look at the people you got to put up with.
Seriously, man.
Let's try number 12. Number 12 has all of our favorite things. So, number 12, I mean, it just doesn't get much better than this, right? We got sine, we got cosine, We got pi x, we got pi y. Everybody likes pi. We got a quantity with an exponent on it.
Fairly upset about it.
All right. First, think of this as u. So the first rule we use is the chain rule. So that will be, if we've got u to the n, it'll be n times u to the n minus 1 times the derivative of u. So 2 u, oh, sorry, you didn't even see that.
Whoa, what get rid of that, please? I'm not ready.
Yeah. That's like looking at Medusa. I'd kill it right there. So we've got 2 u, right, that whole big quantity, to the 2 minus 1. 2 minus 1 is almost always 1. And then the part that kind of scared you a little bit is the derivative of u. You with me? All right, so now our task is to take the derivative of that quantity. So, times. Now, this isn't so bad. Small chunks, okay, small pieces. The derivative of the sine of pi x. We've been able to do this for a while. The derivative of the sine of u is cosine of u times the derivative of u. So we have a new u, don't we? A new and improved u. So the derivative of the sine of u is cosine of u times the derivative of u. So cosine of pi x times the derivative of pi x. All right, so that was okay, right? Slow, deep breaths. Plus, and now we get to take the derivative of the cosine of pi y. Okay. Two things make this worse. Cosine, because everybody leaves off the negative. Okay. And then the u contains a y in it. So, to find the derivative of the cosine of u, it's negative sine of u times the derivative of u. So, negative sine of u. What's u in this case? Pi y. So negative sine of u. Now we got to take, we still haven't done this, times the derivative of u. So u is pi y. Constant multiple rule. Pi is a constant, y is a function. So what is it? Pi y prime. Constant multiple rule. Pi times the derivative of y. Equals 0. The fun has only begun.
No.
All right. Now, let's see here. I'm pretty happy with the way things start off. I'm happy with the 2. I'm happy with everything in that first parentheses. But then cosine pi x with a pi after it is awkward, so put the pi in front. And then all of this, the negative sine pi y times pi y prime, leave the negative in front, move the pi in front, and then I'm okay with sine of pi y. Put the sine of pi y in parentheses, though, because you know what's going to happen if you don't, right? You're accidentally going to group that y prime in there with the theta portion, and you will miss the rest of the problem. Don't do that. All right, now, we got to get y prime by itself. Where is y prime?
Right there. On the right.
Is that the only one?
Yes.
Okay, good. So, the first thing I'm going to do then, and let's see, how do I want to do this? If I divide, I don't have it written quite right on my paper. If I divide both sides by 2 sine of pi x plus cosine of pi y, so I can do this.
Oh, yeah. Oh.
Oh, you kind of like it now, don't you?
It's okay.
1 over.
Now, when I divide 0 by the same thing, I get 0 on the right, don't I?
Yeah.
Okay? So see, I didn't have it quite right on my paper because I forgot to write it down up here.
You can basically do whatever you want.
So I divide those out. That gives me a 0. So I've got pi cosine of pi x minus pi times sine of pi y times y prime equals 0. Well, not yet, I'm going to. All right. So even though I didn't have it, I just forgot to write that part down again right there. All right, everybody with me? All right. Let's keep working on getting y prime by itself. So what would we do next? I'm not ready to divide. I'm not ready to factor. Yeah, look. Because listen, before I divide, before I factor, before I do anything, don't I need to get the term with the y prime by itself? So this term has to be subtracted from both sides. Like so. Yeah, I'm going to the next step because the next step I'm going to do is I'm going to divide both sides by negative pi. And I'm going to divide both sides by the sine of pi y. Yes? No, you can't mix and match your thetas. Well, that was fun. Wasn't that fun? All right. You still with me? Everybody still breathing? We're done with that problem. Number 47. Implicit differentiation really gets fun when you take the second derivative. Y prime prime. All right. All right, I knew calculus was difficult, but y'all have actually, yeah, something snapped. All right. You know this. What's the derivative of x squared? 2x. Oops. Oh. Okay, and then you know what comes next. All right, copy down the minus sign. then the derivative of y squared is 2y, y prime. The derivative of u squared is 2u times the derivative of u, so the derivative of y squared is 2y times the derivative of y.
Yeah.
It's the chain rule.
Yeah.
Nothing more, nothing less. And the derivative of 16 is 0. All right, solve it for y prime. So I subtract 2x from both sides. Then I divide both sides by negative 2y. So negative 2x divided by negative 2y, the negative 2's divide out. I get x divided by y. All right, so hang on before you start complaining. That's true. You never stop complaining. We good? All right. We're supposed to find the second derivative.
Do it again.
Well, the derivative of y prime is y double prime, so we're good there. Charlie? That's the notation for second derivative. There's a reason, and I don't remember it. I've explained I don't remember it. All right. Quotient rule, bottom, y, times the derivative of the top, derivative of x is 1, minus the top, x, times the derivative of the bottom, y prime, over the bottom, y squared. This is one of the easier problems tonight.
Well, that's good. I'm not sure why.
It's a quotient. I mean, you know, now normally it would be something like, you know, that, but it's a quotient because x is x, y is a function. That's what we got to do.
Would you not substitute x and y for y prime?
All right, yeah. See, now we got a problem, don't we? Not only do we have an x in our second derivative and a y in our second derivative, we got a y prime in our second derivative. Well, that's not cool. So what do? Hey, we substitute. All right. So replace y prime with what it equals.
Okay.
And now that gives us another problem. We have a fraction in our fraction. But only for a little while. Since the denominator of our fraction that we don't want is a y, multiply by y over y.
I was just kidding about this being the easiest problem.
No, really. This is one of the easier ones. Y times y is y squared. Y times this, the y's divide out, leaving you with negative x times x. Y times y squared is y cubed. I don't think I'm multiplied by y. And if you get that far, you're really pleased with yourself, right? You're going around, you know, you're doing the high five thing, and if you got any muscles, you're doing the muscle thing, and right, and you know, in your face and all. And then you try to prove to your friend that you're correct, and you look in the back of the book, and the back of the book says the answer is negative 16 over y cubed.
That didn't happen.
Yeah, it did. And it happens because if x squared minus y squared equals positive at 16, y squared minus x squared must equal. Yeah, that's what I had over here. How else does it work?
I don't know.
Can you just leave it that way?
You can leave it that way.
Okay.
I'd rather you not.
Okay.
You're saying that normally. Jumping up and down.
Anytime you can substitute, do it.
Oh, it's storming outside.
All right. Listen to me. We don't have enough time to do number 59. So, I'm doing this so that it's on the video that you can watch tonight to get it. Watch how I scroll neatly down.
Really?
Go back. Oh.
Oh my
That's really good there. Oh, that makes sense.
And then I go back up
Hey, do it again.
for you to get a look at the first half. I pause for a moment. Then I move it down for you to look at the rest of it.
Tangent. Perpendicular.
And then
Yeah. Circle.
I give you the assignment.
That scares me. You're making me sick.